Hello, good morning, and so welcome to the next session. So today I want to basically talk a little bit about cognitively enabled robotics, where we are and where we are going. I think these are kind of topics that doctoral students who want to contribute to the field of robotics have to think about, right? And I think it's very important that if you think about what the contributions of your dissertation research are, that you're able to locate your contributions in the overall fields, just to kind of make that you can claim that your contributions are important and that they are difficult, and more explicitly state what your contributions, technical contributions, exactly are. Okay, so just to set the big picture, right? So I think a good picture for where we want to go is that robot that can basically survive in our household and accomplishing household chores, and this over the lifetime of a robot agent, right? And we have seen in the first lecture that if humans kind of control robots through telepresence, so the robot bodies and their basic control mechanisms can do a fairly good job in doing that. We've also seen, and I think that's kind of one way of looking at that, is that we are looking at a particular task, such as fetch and place, and we look at a particular context, namely what we call the ETH Robot Day, and we look at the tasks of setting the table, cleaning the table, loading the dishwasher, unloading the dishwasher, putting things back into the cupboards or in the trash, and do that kind of over 3 times a day for breakfast, lunch, and dinner, and do it over the lifetime of a robot. That's kind of a still quite narrow task, but it has a lot of variety in it, and you need to understand a lot in order to accomplish it, right? And question that arise in this context is, so if we have that basic program that can set the table, what happens if we run that robot over the lifetime of a robot? It collects experiences, maybe in the form of names, uses these names in order to specialize itself according to the specific fetch and place task it has to accomplish, and to speed up its reasoning process in order to get a better performance, right? And I think that's kind of, I think, a very ambitious challenge, and I think that's kind of one of the directions where we have to go. The other dimension that I think is very important is dealing with the open world and the open tasks in our world. So if you're looking at a boring task, so eventually what you want assistant robots to be able to do is pouring any substance from any source to any target and for any purpose, right? And that's an amazingly broad skill. And the question is, how do we kind of program robots for doing that? So one way kind of that might be a plausible way is that we enable our robots to read instructions, maybe in the World Wide Web, on web pages like WikiHow, to watch instruction videos, right? But being able to learn from these instruction videos and a language instruction is again kind of an extremely ambitious task. So if you look at that, right? So if our robot is watching that video, we have in the video a different agent with different capabilities. We have different objects. The objects have different physical properties. We might have different tools in these videos. And if the robot wants to learn in this setting, just from in one trial, then it has to understand why what it's seeing in the video is working and what is essential in that video to make the task succeed. It has to be able to transfer these task essential or task critical motion specifications and basically transfer them to their own setting. And again, it has to now apply the task to different objects with different purposes. It doesn't know exactly the physical parameters of many of these entities. So for instance, it has a kind of limited knowledge about the viscosity of the milk inside the milk box. It doesn't exactly know how much the milk box is filled. And yet we want to have a kind of the generation of a robust control program that is basically transferring knowledge from a completely different setup into a setup which is only partially known. And I think that's kind of something that we have to be aware of, that this is part of where we need to go. The challenge becomes even bigger when it's not only our robot performing a task, but now other agents are part of the environment, right? And now what the robot control program has to do is not only achieving a task, but achieving it by leveraging kind of maybe the human as somebody who can help achieving the task. But there are kind of new dimensions of the problem coming into it, but because now it's not sufficient that the robot accomplishes the task, but it also has to guarantee the safety of the human. I think there are all these ethical, legal, and social aspects that put additional constraints on the behavior of the robot, and kind of the same complex program, which is achieving the robot's task, basically runs in the other agent, and this program then has to guess what are the intentions, what are the capabilities of these other program running in the other agents, in order to have something like competent cooperation between humans and robots. And I think that's kind of a huge step going in forward. So you might think, okay, now these are kind of very complicated robots. They are kind of general purpose things, and well, I only look at kind of much simpler robots and simpler tasks, so I don't care. I don't think that one can make that case, because if we are looking at what the robotics community has to deliver, we have to kind of implement and deliver and deploy many different robot control programs, right? And those robot control programs have to run on different robots. The robots have to act in different environments, and they have to kind of accomplish different tasks. So if we go and we write programs for each combination of task, environment, and robot, we have lost, right? So there's no way that with the existing number of robot engineers, software and designers that write robot control programs, we can achieve this kind of this number of different control programs that we have to. So we have to have mechanisms that help us to develop these different applications in robotics much more efficiently. Right. So we have also pushed the point, so both in the introductory talk, also David Vernon on cognitive architecture, that the essence of intelligent agency on robots is mapping task requests into specific body motions. And I think that's kind of true for any robot, right? The push for having more complicated, more kind of complex and sophisticated programs comes when we change the quality of the tasks that we put to a robot, right? So if the only task of the robot is to be a vacuum cleaner that has to cover kind of a room, things are fairly okay in terms of complexity. But what happens if we go towards much more complex tasks? Whether we change the tasks the robots have to accomplish, if the robot has to do multiple tasks at the same time, if the tasks are not only kind of selected from a set of previously known tasks, but the robot also has to learn to perform new tasks, and it has to perform the tasks in open environment. And the tasks are not spelled out explicitly as a concrete objective function, but they are vague and underdetermined. Each of these properties of the tasks, they force us to kind of design and realize robot control programs that have additional capabilities. And that's where the need for cognitive capabilities of robots come in. So when this is essentially our challenge, basically having robots to kind of accomplish tasks in the environment, then the question comes, how do we measure that we are actually successful, right? And here we have the standard model from Russell Norvig. And so essentially the argument here is, so we are observing what the robot is doing in the environment, and the recording in the environment is giving us a state trajectory that the environment is going through, and we define an objective and a cost function over that state trajectory that gives us a value of how well the robot is accomplishing the task, right? And so what AI is then aiming to achieve, it's trying to find the function that has the highest expected utility with respect to this value, right? And in your traditional AI book, this is kind of the only criterion that is applied to robot agents to measure how well they are doing. So, however, if we are thinking about the robots that we were just thinking about, the game is a little bit different, right? And the game is different because kind of these objective functions, they can't be run on episodes because our robot agents have to operate and achieve their tasks over their whole lifetime. And that changes the game a bit. So in that case, kind of the quality of the program that is controlling the robot does not only depend on how well it does on specific episodes, but it's also, depends on how well the program prepares for all the other tasks, for all the other environment conditions that it hasn't seen yet, right? So it's in this case, when you play the Infinite Horizon game for robot performance, you have to prepare kind of for all the things you don't know yet and that lie outside of your training examples. And that kind of what forces you to generalize or to require your programs to be composable in order to solve new. So the way that we can basically test these capabilities, that we can transfer from pedagogics and the way how students in school and later are tested with respect to whether they have learned a particular topic or not. And a very famous way of trying to get more structure in this assessing this understanding is Bloom taxonomy. So and the idea is that you're structuring your problem-solving capabilities in different levels of hierarchy of cognitive competence. And at the lowest is simply things like knowing and remembering. Then you have to understand the things and what is going on. You have to be able to apply what you have understood to new problems and tasks. And on top are things like being able to analyze your own performance, being able to evaluate how well you're doing, and basically creating new solutions for new tasks that go far outside of what you have learned so far. And what makes that taxonomy effective for us is that they have developed question templates that are specific for these different levels of competence. And so the question is, can we take these question templates, can we transfer them to robotics and use them to evaluate how cognitive our robots really are? So I think that's kind of interesting and would help a lot to understand our field much better. Okay, so that's kind of about the challenges, right? So that we want to have these agents accomplishing very complex tasks that change, that are vaguely defined over their lifetime. Kind of we are restricting ourselves to tasks that can be accomplished by body motions and their physical effects. And we want the systems to evolve that competence of solving manipulation tasks over their lifetime, right? So if we are looking at our field, we have seen many big ideas and that help us to push our understanding of how we can write programs like the ones that solve these challenges, right? And I want to basically look at them in 3 dimensions. One is in terms of computational paradigms or computation models. A second one in terms of principles and conceptual frameworks. And the third one in terms of cognitive capabilities. So in terms of computation models, we have seen, in particular in AI, lots of different paradigms that kind of were used in order to make robot control programs or AI programs in general more competent. So we have learned about physical simple systems, right? Where the basic idea is, if you can completely and correctly axiomize your task and your task domain, then kind of a very simple computer program, which is a theorem prover, becomes a problem solver. So it kind of, the idea is that it scales towards all the tasks we have seen in that in our challenge section, right? And that's kind of a very powerful idea. So the second computation model that arrived in AI was the idea of problem solving as heuristic search, right? So that you can look at solving a problem as a search for a solution. And if you have heuristic knowledge that guides your search, then you can basically improve the competence of your system, right? Kind of one of the following paradigms was expert systems. So that were knowledge-intensive problem solving, kind of where the slogan was, "In the knowledge lies the power." And there it was basically getting expert knowledge into the system in order to configure complex systems like computers or diagnose diseases. And you did that by basically putting lots of formally represented knowledge into the systems. Then came artificial neural networks with the argument that's how the brain works, evolutionary programming, kind of that's how evolution worked. I think there's another paradigm, probabilistic reasoning, then certainly problem solving as an optimization of objective function you can see very often. And now we have the phase of data-intensive machine learning and deep learning. So if you're looking at all these computation models, right? So all of these models kind of all but the last have run through this sigmoid function, right? Where basically in the beginning, kind of the methods were extremely cool. They looked as they would scale exponentially, and then one noticed that not everything is so cool, and kind of it flattened out, and kind of there was an asymptote of the kind of performance that you can reach, right? And yeah, so you can guess at the moment whether when you look at deep learning, you're really at this exponential curve, or whether it's yet another method kind of that has some asymptote kind of that it can reach, but also its limitation. So I think an important lesson that we have learned is that basically these methods are very cool for some things, but they don't scale for being these completely general problem-solving paradigm. Is actually a strength and a weakness, right? So Ian Horswell once said that computation paradigms or architectures become powerful because of what they can do, what they cannot do, right? And the reasoning behind that statement is only if you make the commitment kind of that you don't want to basically be good at some aspects of the problem, you can basically exploit that in order to become much better in other domains, right? So kind of physical simple systems are good because you can enable systems to make semantically valid conclusions without requiring the systems that they understand kind of what they are reasoning about, right? And so I think that's kind of a very cool strength, but we also have seen that kind of that paradigm has its weaknesses, right? When it comes to uncertainty, when it comes to that we require the representations to be predefined and applicable to all problems that we want to solve in the future. And here we see that data-intensive machine learning, where you kind of learn the representations, have big advantages, in particular if it comes to tasks like perception and other things that that seem to be much better behaved if we don't make the assumption that we can explicitly state a compact symbolic representation, right? So the lesson that we have, I believe that we have to draw from that is that if we are looking at a generally intelligent system, kind of with the brain being the most inspiring computation device, right? So then it's very likely that systems with that performance rely on the combination of different computation models that interact in synergetic ways in order to solve problems that are so hard. I think it's naive to think that the challenges that we have talked about can be kind of tackled just by looking at one single paradigm. So that's kind of my personal opinion. Okay. Okay, so the second dimensions are principles, and I think we have seen some of the very cool principles in this fall school, right? So I think the first one by Martin Beetz, the free energy principle, that you can look at what you want to do is essentially you want to basically optimize your capability of reaching the future states that you want, and you can basically use the free energy term in order kind of to measure the expected divergence in the future states that are basically, that is caused by your policy that you want to execute. And you kind of have that other term which gives you the expected future uncertainty if you're executing your policies, right? And I think, I mean, every scientist, I think, gets wet eyes when when you basically have formulas that are so compact and try to explain so much, and so it's kind of very cool, right? But one also has to keep in mind that this free energy principle is only kind of one perspective of the problem solving skills that cognitive agents, cognitive robots need, right? And we have seen other things. So I've talked about that a computer program is not only a representation that specifies how a computation is be done, but also that communicates the ideas about how to solve problems back to the person programming the computer program, right? And that this is an important observation if we want to develop computer programs that scale towards our challenges, so that kind of if our ideas change, we want to basically generalize our ideas or apply them to new problem domains. And we know that controlling a robot body is something that is extremely complicated, right? The other things, like so if you're comparing what deep learning is doing at the moment, it's mainly trying to learn how to kind of realize a specific function. So there are other ways to look at what learning systems should be doing. In particular, if you compare today's learning systems with the way people learn and think, and also in particular kids, right? So kind of another direction is building machines that learn and think like people, and which is kind of something that is pushed by Josh Tenenbaum. And here the big idea is that learning is actually model construction. It's not kind of trying to kind of learn a specific function, but you want to learn a model that explains you how the world works, and that helps you to solve all the problems that you are facing in the future, right? And here, I think the problem of free energy comes back. So this is stereotypicality, or David was mentioning manifolds as a powerful problem-solving paradigm. So I think the big insight is, if we are seeing that our brain is solving computational problem that we in computer science see as intractable or unsolvable, then I mean, there might be one explanation that theoretic computer science is wrong. But I think the most likely explanation for that is that nature has managed to reformulate these general problems into more specific problems, which are much, much better behaved than the general variation. So if we are looking at just doing motion planning in order to pick up plates and put them on the table, if we would use the randomized motion planner, there would be much, much more entropy in the behavior for doing that. Kind of, it's probably that these randomized planners could also find trajectories that are better, more efficient than these stereotypical ones. But even if they are a bit better on this particular episode, there is a huge advantage in basically acting stereotypically in the world, right? And the reason is, if you're acting in a stereotypical manner, your entropy in behavior is much lower. This helps you to diagnose more easily if something is going wrong. You can learn faster. You can also basically, if somebody else is doing something like that, it's much easier to transfer what you're seeing in what you can do. And also, if humans act in that stereotypical way, it's also an important mechanism for implicit coordination, because it allows you to predict how somebody else is completing an action, right? Another principle is end-to-end learning, right? So we have learned that if you have huge amounts of data, you can specify the problem that you want to solve kind of in objective function, and the objective function is differentiable, then kind of a very cool way of learning a particular competences is just throw data at the problem and optimize your solution, right? Let's skip that. The third dimension that I briefly want to talk about is the issue of capabilities, right? So if we are looking at the human brain again as our main inspiration of how we might be able to develop intelligent robot control systems for robots, we can also see that there are functional components in the brain and capabilities that seem to help a lot in order to build the kind of robot control systems for our challenges. So one of the capabilities is certainly prospection. So David was talking about that, right? And kind of the idea is extremely old. So here, for example, Craig I think 70 years or almost 80 years ago, he says, if the organism carries a small-scale model of the external reality of its own possible action in its head, it is able to try out various alternatives, conclude which is the best of them, react to future situations before they arise, utilize knowledge of past events in dealing with the present and future, and in every way to react in a much fuller way to emergencies which it faces, right? So I think, again, so if we want to have robot control systems that are capable of accomplishing novel tasks in one try, I think prospection has to play a huge role in that act. Again, David in his talk was also talking about memory. Memory, I think memory is much more than a knowledge base, and I think it's so for one thing is that memory, as David pointed out, has that huge constructive component, right? It's kind of the famous saying, it's a poor memory that only looks to the past, right? It kind of memory is actually, the main purpose is acting more successfully in the future. And so I think building computation models of memories, right, that enable robot agents to kind of not only learn from a specific set of training data, but that gives you essentially access to your whole experience over the lifetime in a manner that you can retrieve the information you need to solve the current problem, right? Another powerful idea is the idea reasoning with eyes and hands, right? So we were talking about reasoning in terms of reasoning with symbolic representations that are very abstract. But Patrick Winston made that argument. So how likely is that nature basically has developed all these cognitive capabilities for successfully acting in the world, and then forgets about all these capabilities when it comes to higher level reasoning, right? And I think one area where that idea comes up is essentially the simulation theory of cognition, that you can mentally imagine how you solve problems with your eyes and hands, that you can imagine how situations look and what the consequences of actions are before you kind of do that, right? Other important capabilities are understanding what one is doing, metacognition, affect-aware motions, and I think it's just kind of a selection of these capabilities. Okay, so that kind of brings us to so what? So we basically have these huge challenges. We have these big bags of very cool ideas, right? And I think the big challenge we are facing at the moment is that if we want to meet the big challenges, we basically have to put together all these different computation paradigms, these principles, these capabilities, right? And the big thing is, and the thing that makes it so complicated is that these ideas are not isolated, right? They all play with each other, and the interplay of these different things, this is what really makes kind of agency competent. So here's, I think, my favorite roadmap for artificial intelligence, and I think that's kind of the first roadmap that I have seen that brings these ideas very much to the front, right? So it essentially says that the next 20 years of AI research, they should focus on three important topics, right? And they are integrated intelligence, meaningful interaction, self-aware learning. And so kind of the integrated intelligence is composed of a science of integrated engine. So it's not, building systems is not an engineering task. We have to understand how all these things can be integrated together in order to solve our challenges, right? There's contextualization, but also we need open, extensible knowledge repositories with heterogeneous knowledge, reasoning at huge scale. We need to mechanisms to capture knowledge, integrate, and refine it. And I think it's the reason that I find this roadmap so inspiring and in my opinion also pointing in the right direction is that it's acknowledging that the kind of competence we want to build into agents is the combination of many things, and we have to understand how these things work together. And this is kind of the reason why we find cognitive architectures to be such an important research topic to work on. And CRUM, as David pointed out, it's very limited, but I think one can see at different places where some of these interactions of these different ideas are implemented, and one can also see how they actually make the programming of the robots easier, and that you get for kind of stories of how you can tackle some of the challenges that I have listed. So I think the kind of where we want to go is we want to have these architectures as an interface layer for our research, and we basically want to have the concepts. The concepts, they have to reflect these different programming paradigms, the principles, and the cognitive capabilities, and how they interact with each other. And I think that it's very cool. We make very good progress if we can explain the operation of these architectures in very compact ways, and we can validate that if we are implementing robot control systems according to these architectures, that they are better with respect to some of the challenges we have seen. It's important that even if we have these architectures, there is all kind of research can go in and can be used to implement these architectures, right? So you can also take different components of the architectures and implement them together. In the worst case, you can basically say, oh, my whole architecture is just one big system, and I want to have one deep learning network that is doing everything, right? So that's kind of an extreme case. But I think thinking in terms of these architectures will help the research field in order to understand what everybody is working on, how the things fit together, and whether that research is useful. I think it's a question is whether using these architectures allows us to realize robot agents that scale better with respect to the challenge tasks that I've listed in the beginning. Okay, cool. So this is all what I wanted to say, and I'm happy to answer questions as far as I can.